Now, if we're going to part of the same, other numbers that are not rational. The word rational has the word ratio, fraction, ratio of two integers. Other numbers that are not rational. They actually are. It's possible to prove that if x squared equals 2, then x is not rational. It's called irrational. It doesn't mean it's a crazy number, although we chose it that way. It just means it's not represented as a ratio of 2 integers. Non-rational. So it goes, the first person to discover irrational numbers got thrown overboard. The Pythagoreans and the Pythagoreans were like, so mad at this, they threw overboard. Oh, what about irrational numbers? But then after they threw overboard and died, the story says, then they realized it's right. We call that, I guess. They didn't like it being non-rational numbers. So, we're going to prove this as well, that all those ratios will be proved. But 2 really exists, the square root of 2 really exists, this pi really exists. Right? What's 10,000 meters of pi? There we are. 10,000 meters of pi there. If you want to memorize pi, use that there. I never bothered to memorize pi back here. This is not what it is. Well, I suppose in eternity you can have it does illustrate the infinite richness of the universe. There's a negative meter of pi that you can never get. I don't know if I want to, but I could. You don't have to go down and be better. Million digits? Or is there million digits to square root 2? We'll do it. I guess so. Well, we have million digits. Actually, I don't know for sure it's million digits. Look at it, maybe. A million digits for square root 2. Square root 2 is also irrational. So there's million digits to all these for square root 2 as well. But wait, how do you know the square root number 2? We're really going to square this number? In fact, we're only looking at the first million digits. What about the first million digits? The digits go on forever without looking at it. How do you know the first number of the square root? It's actually an issue. Actually, in a female math course called Your Analysis, we proved there is a number, but you don't work with the decimals because that's just anyway. So we use something else. There's a different strategy to prove square root. You wonder about infinity? Have you heard of Zeno's paradox? Anybody ever heard of Zeno's paradox? Sorry. What's happening with these numbers? When I have the higher and higher power, they're getting closer and closer to 0. Right in the fraction here, but they never equal 0. Just like Timo thought, I wonder if motion is constant. And people start saying, okay, don't we move? They said, well, that's pretty much practicality of the fact that you see moving. Let's just think about it. If I were to move from here to touch that board over there, well, to get there, I have first have to cross half of this. And then I have to cross half of this again. And then half of this again, half of this again, half of this. How am I going to get there? I have probably half of this. In fact, it requires any even tiny amount of motion. How am I going to move my finger from here to here? Because from here to here, then I got half of this and half of this. Well, how do you say you move? Okay. So we want to become resolutions like our doctrine. What is it? I don't think I want to answer because we may have to be patient about motion and time and maybe some physics with a lot of mechanics. I don't know. It's not interesting thing. Does 1 100 being equal 1? How many people say yes? How many people say no? A few souls who have that sort of thing. Actually, 1 100 being equal is yes. 1 100 being yes for 1. How could that be? So, sometimes people get big enough for it's a little algebra. But x equals 0.9 review. And then that means 10x, I guess, is 9.9 review. So I guess that means if I subtract these two equations, I get 9x equals 9.9 review minus 0.9 review, which I guess must be 9. So that goes by 9, x must equal 1. Whenever they prove well, a little bit whether this algebra is the way we allow it the way it is. But it seems beautiful. Here's my favorite proof. Why is 0.9 review equal 1? I hope I don't prove. Well, if 0.9 review do equal 1, they different. There must be something between them. What number between them? See, you can't find any number between them. Done. They must be the same. People sometimes come back and say, well, is it 0.9 review? And that's a really have a 5 or that? The 0.9 represents for 1 forever. You can't go 5 again. Now, here's that's what I should have taken. Remember, it's positive independent decimals. You know, it's quite very good. The idea of numbers is independent of how you represent. In fact, any decimal that truncates, like 4.7563, has 2 decimal representations. Well, you could also do a bunch of zeros after that point. You can also write it as 4.7562999999 words of my power. So the table. Which brings me to a little story. Almost like examining with me. A little story about me, actually. And my son. My son didn't believe that 29 routine was one. And I said, hey, look, it must be true. Because you know what the age was. And my son's like, yeah, I know where the age aren't always right. I'm like, yeah, well, they're mostly right. Started reading, doing this and thing. 29 routine, written different ways. 10 shows you down one. 2 different ways to represent the same number. It's true. And I do this introductory section, and I remember this one. It says the equality, 0.9 routine has one that accepted by mathematicians in part of the math like this. And my son was, yeah, aha! Guarantee one that accepted doesn't mean it's true. It's just accepted. I think it's false. And I said, no, why do you read it that way? So I created my Wikipedia account. That helped me sense. And I edited this one sentence. I said, the equality 0.9 routine has one that accepted by mathematicians, and it was actually true. In 10 minutes, somebody had believed it. We're going to see if it's first step. I think I'm a troll or something. No! There was no reflection of my son's mind there. I shouldn't say accepted. It's true. Okay. So they're not a little confused right now. One's not having a little confused. But that's a true story. Happens all the time. Alright, I'm getting low on time. How should we end here? We'll link to that story in this class. Yes, they will be. Sorry. No, we're not in the main focus. So necessary though. Got Bible verse here. There's a whole Christian school. I don't read Bible verses in just to pick Bible verses. I want to emphasize something. And this is one of my favorite verses. Find values, whatever is true, whatever is honorable, whatever is just, whatever is pure, whatever is lovely, whatever is commendable, if there's any excellence, if there's anything worthy of praise, think about these things. Not only does that thinking about God and saying everything great about that, but also both true and what I do about God and sure and worthy of praise. It helps me give us money to think about it and use it, and that's really cool. Like that. I didn't put this on Moodle, and again I put the installation instructions. I would encourage you to look over once I put this on Moodle. Some of these things that I want to time for. You guys are going to get like clicking somewhere and selling with them now, and doing shift return, and you'll see some, I think, cool things. What does this thing illustrate? This thing illustrates that the inverse function of y equals x squared, so the means to restrict the positive numbers. Every single time by reflecting across the line y equals x, here's the reflection plane. You see the reflection happening across the line y equals x, you get the graph of y equals square root of x. So that's how the simulations can be like that, to illustrate these ideas. I got different topics listed as a review to now. We'll talk about them a little bit more on Wednesday. And places that we're going. Where we're going to have those two in the section here to open it up. To see where we're going. We'll talk about these things along the way. We're going to use ourselves. The last section, we are a list of in-depth numerals you should memorize for the kids in class for the 3 on Wednesday. Take the rhythm of FDN and FDN plus 1 over plus 1 plus E over 3 plus E. That's true whenever I'm getting 1 with these like this. So there, when any of the 1 is an after log, or the after value that's supposed to be our most general form of the derivative. And it will be the x is the x plus e. Careful with your trig function, the integral of cosine is sine, not negative sine. So the derivative of sine is cosine. And the integral of sine is negative cosine. Careful there, because the derivative of cosine is negative sine. So you gotta be careful about that kind of thing. Here's what we're able to memorize for this quiz. Choose a marker. For example, arctan of x and inverse tan of x are different notations of the same function, and neither one of them is 1 over tan of x. You know, the 1 over tan of x is 4. Cosine of x. We don't need either notations, okay, you're saying it arctan of x. And you should know that if any of the rates are supposed to be okay, so quiz on Wednesday will include a couple of integral problems you should look at memorizing. Alright, that's it. Alright, so second day of class today, Wednesday, just a reminder that one day, of course, is Labor Day, so we have a day off. But also want to remind you that we have a meeting exam coming up now in 12 days. The meeting exam is again on chapters 5 and 6, which I'm not explicitly going over in class, so I will go over it as I go through chapter 7. So I will review chapters 5 and 6 as I go through chapter 7. And actually, I'm starting right now. I will do this one day. One of the exams is going to be half the exam, like half the grade. The questions are going to be pretty similar to those problems. That's going to be in chapter 5 and in chapter 6. I put the key on chapter 5 yesterday. I'm basically going to take those examples and change them over a little bit. Yeah, so,
Is there any way you can put the textbook online for a bit, because the bookstore is out of books for this course?
I'm not able to. The publisher doesn't do that unless you actually buy an access code, as far as I know. So they still run the books morning?
I did. I filled out one of those yellow slips, and I'll get an email when they come in.
Okay, I'm sorry about that. I didn't know it was going to happen. I think the best I can say is try to find somebody to work with in the meantime, and then hopefully they'll come in, and if necessary, maybe you can see if you can find a used copy from somebody. If you can ask around, somebody may have it. There are a lot of used copies floating around. Okay, I can find it. Let's look at a little before we get into the content again here. So I did put the solution key for chapter 5. Zoom in on that. I will put the one for chapter 6. Probably tomorrow. So these are the end of the chapters. You solve them time to get yourself half a dream. And just working on them as much as you can to help you probably need it. We're going to be doing the same questions, similar to a random sample of each review problems. Okay. Down in all the review problems, I'll take them. Okay, so I gotta take a certain number of them, maybe 4 of them or something. Put up the mini exam, and that would be what you're testing them. I did put the lecture one mathematics on the book. So once you've got mathematics installed, you can download that and you can listen to the class. You can see what I did. Re-enter the code if you like, just to see what it does. You will be using mathematics to some extent on homework. And so you are going to want to learn the basics. I'll try to focus on basic things that you should know how to do. I would use harder things too, like some of those things I showed you last time. You won't be able to use basic things that I'll show you from my highlighting class. I'll put today's up there later today, and I can download those. I guess as far as the version word, I think I recommend either 10.4 or 11.0. 10.4 is what's going to be on Double's computer. Perhaps that's the best one to take if you haven't done that yet. If you have trouble with the activation code, email Eric Gossett, GOSSETT, at apple.edu. GOSSETT, at apple.edu, and ask him to complete the activation code if you have trouble. Links for lecture video will be up here, so I've got that statistics one, and also the first lecture is up here now. I will post today's lecture up there today. The couple most typically need to watch. It's maybe once in a while, you have to go, for some reason you can watch it forward if you didn't quite understand something and want to watch it to do that. I'm doing this for a couple purposes, just in case I want to just flat out lay in the future, and just in case I want to maybe do some group work in class. I can watch the lecture and then do group work in class. Those are the two reasons that many of the lectures that you don't want. Alright, if you don't want the back of your head in the video, if you prefer, pinch over the other side something. Most of you are over here. Most of you will probably can't see it over here, also you can camera. That's fine. We have 2 online quizzes too. We have an in-class quiz today. Halfway through the lecture, we'll take a break, take a quiz. Maybe 5 or 6 minute quiz yourself, hopefully. And you don't want to take a break, just a stretch or maybe months back or something real quick. And then we'll start the second half of class. There's going to be a lecture A and a lecture B. I should also probably point out that up here, besides the mathematical installation instructions, this is a link to a video tutorial on Mathematica that will go in. Don't do the free-form linguistic input. Mathematica can try to interpret what you want to do. But we want to try to do correct syntax because that'll help us do better things. So we can be more careful at the start. We can be more fancy later and not make mistakes. And this is a file that's got some suggestions for you to use this sort of What's lecture A going to be about? Integration by substitution, both indefinite and definite integrals, and their relationship to the fundamental physical calculus, and actually also the change of say. So you actually have that. And the change rule. That's going to come this way too. And then lecture B, we're going to apply these ideas to some applications, probability, motion, area, and average value. Alright, so let's do some examples. We'll kind of start maybe as simple as we can here. So we want to integrate 2x times x squared plus 4 to the 10th power. Let's come up with a video. Yeah, okay. Okay. There's actually 2 strategies to use. You can try to expand x squared plus 4 to the 10th power. Right, you multiply it all out, and then multiply everything by 2x. And then integrate. Or use what's called a substitution. And the substitution rate is definitely there. Because if you have to expand this out, expand something to the 10th power, this is called a binomial. You usually have a binomial theorem, which maybe you recall involves using Pascal's triangle. And with the 10th power, you have to go way down Pascal's triangle and look at the coefficients. Or you could use combinations of that to help you expand this completely. I can actually have that pretty good real here. Just to show you how nasty it would look. Let's go ahead and expand out this thing. This program, 2x times the parentheses x squared plus 4 to the 10th power. Actually, if I just enter this additive, I'm not sure if it's going to expand or not. I might have to use a command. Let me just do enter. It is not expanded. It's just the back of it. All right, to expand it, there's a command, a built-in function called expand. Built-in functions in Mathematica, you should know, always come in capital letters. And an input is always going to type square bracket. Expand is an example of a built-in function or command that will take this expression and expand it. There it is. Yes, you don't want to have to do that by hand. You could if you give yourself enough time. You can expand this and integrate that. There's a better way. Substitution. Many books use letter U for substitution, and we call it U substitution. Our book purposely avoids letter U. The other reason for that is because the letter U also comes up in something called English type arts, and they want to avoid confusion with English type arts. They use letter W. There's another good thing about using the letter W, so U, that will come up in a few seconds here. You want to know what's a new variable, U or W. It doesn't matter what you do under homework. You use D if you want, doesn't matter. You want to put the letter D, in this case, this expression inside the parentheses, that is the other way you have to expand. How do I know what's the right thing for WD? Well, partly because you often try to guess when something in parentheses like this to a big vowel or maybe some type of cosine function or sine function. Often that's a good guess. However, it's not always a good guess. You also want the other thing, the other factor of your exam, to be either the derivative of what W is or maybe a constant local to. If this is W, W is x squared plus 4, then 2x is the derivative of that with respect to x. That's good for another substitution. And here's where it gets funky with letter W, because you use letter W here, and you find DW, DX, that's kind of fun, because it says, hey, Arthur, DW. I love Arthur. You know, my kids are now in their early 20s and late teens, and they don't watch Arthur. I love watching Arthur. DW, DX, instead of UDX. So, let me read the W. DW, DX is a little bit of W with respect to X is 2X, that's the extra factor of this. It's common, and I think a good idea, to pretend now that this is a fraction. It's really not a fraction. It's really not a fraction. The derivative is really a little different portions of one of the fractions, but it takes care of itself, just represents the value of the derivative. It's not really a fraction. But oftentimes it doesn't prove to pretend it's a fraction. This is the right answer, and that's an example of something we're going to do here now that pretends it's a fraction. There pretends it's a fraction, and pretend we multiply those times by the x. To write it this way. I think it's a good idea to do that. One of the founders of calculus, Leibniz, Newton and Leibniz were the founders of calculus. This is actually called Leibniz notation of derivatives. By the way, you spell Leibniz. L-E-I-B-N-I-Z, and it's in German. So E-I times an I, and then E times Leibniz. Say Leibniz. That's Leibniz notation. And if I understand my history right, he actually did think it was a fraction. And there are certain modes of thinking you have where you can consider this fraction, it's not really clear. So I think you can clear, it's really, really high level math that we don't get here. And he took the kind of intuitive approach as well, applying to the addition too. I think you know what we're doing on Chase now, but no one has to do it. Which we do now anyway. We're going to tend to fraction, multiply those by the x, dx, right? And what I've done now, I see that I've already got here, it's w to 10 power, and I also have a dw. The true actually is the same as dw, it doesn't have to be right next to dx, so I could do it. This is going to become the integral of w to the 10th dw. And hey, that was what makes it easy integral relatively speaking. All the time you should be able to do on say quiz. A power function, and the memorized integrals. You can 10 here, I have to add them to that to make it 11, and also divide by that same number. Don't forget your plus c, and the quiz, you should make sure you put the plus c for full credit. Like that's basically the answer equals 2. Include plus c for full credit. On the A, you can plus c, no credit. Get it wrong. So important, plus c. Mostly because we want to allow ourselves to find disintegrating derivatives, solve differential equations, right? We have to allow for an arbitrary constant to solve differential equations. So that's an important thing. We're not done. You have to re-substitute back in terms of x now. W is x squared plus 4. I can either something for the elements divided by 11, or I can write it as 111 x squared plus 4 to the other. Like that board sheet, so much later. You can always check ranges, okay? Differentiate the function and see the different circle. You can circle this, but let's also differentiate it. Oftentimes I write ddx. Next to an arrow like that, if I emphasize that I want to differentiate something, in this case with respect to x, this is sometimes called ddx or derivative operator. Differentiate what you see here, the idea with respect to x. When you get like that, you bring down the 11,